Okay, I had talking about impedance. As I talked, to use the pen. Yes, for the impedance, just as a brief review, for the inductor, the impedance of the inductor will be J omega L. And for the capacitor, it will be 1 over J omega C. So anyway, for the circuit analysis, for the power system analysis, during a steady state condition, instead of inductor, you can use J omega L, and instead of capacitor, you can use 1 over J omega C. And I didn't talk about this as well. R, resistor. For the resistor, what's your propose for the, what will be the impedance of resistor? What's your suggestion? The L, it's not L. For the inductor, Z impedance is J omega L. For the capacitor, Z is 1 over J omega C. So the question, what's the impedance of resistor? I'm waiting for your answer. Can you guess? Can be J omega R or 1 over J omega R?
Does it have omega at all?
So what will be?
Like just JR?
No.
Hmm.
Why it doesn't have omega?
I don't know, because it doesn't have like 90-degree angle, right? Not sure.
No. Other answer?
Is it just R?
Yes, it's just R. Without J, without omega. And J omega, we have in the just in the inductor and the capacitor because of this derivative. This J omega and this J omega is because of the derivative we have in the formula of voltage and current in the capacitor. And the capacitor, you have derivative, and in the inductor, you have derivative. When you have derivative in the relationship between voltage and currents, you will have J omega in phasor domain. However, for the resistor, the voltage is just R times I without any derivative. So when you don't have any derivative in the time domain, you will have no J omega in the phasor domain. That's why the impedance of resistor is just R. But you have J omega here and J omega here. Okay. Okay, it was the impedance. However, how we can use this notation, this definition in the network analysis? In the sinusoidal steady state, when you have no transient, no disturbance in the power system, all the excitation, all the source, all the voltage source or current source are sinusoidal. And we can use all the trick, all the way to evaluation of the circuit you can use in the power system as well. For example, if you learn something in the circuitry, if the power system in the steady state condition, you can use the same analysis method in the power system as well. Just in the steady state condition, non-transient. For example, suppose that if you have a circuit in this way, and for example, it's a voltage source. If the system is without transient, it's without fault, instead of R, you can use R. Instead of capacitor, you can use just J 1 over J omega C. And instead of inductor, you can use just J omega L. And this is a complex value. Complex value. It's a real value, but in a general case, it can be complex value without the imaginary part. And if we can write the voltage source in the complex value, we can evaluate the whole system in the complex plane. In this way, we can make the analysis simpler. However, for the network analysis, we have another notation that is extensively used, that we call it admittance. We talked about the impedance. Inverse of the impedance is called admittance. 1 over Z will be Y. The admittance is another form for representation of the element. Each element, for example, in a general case, we have elements in the circuit. So voltage and the current. Each element can be expressed as a Z or present as a Y. Both of them based on your preference. Suppose that, do you remember the last session we talked about which type of method you can use for the analysis of the circuit? You can use node method, you can use mesh method or loop method, but it depends on your preference. And here again, we can represent the element of each element of the power system with Z or Y, but it depends on your preference. Which type of notation do you like to use? But you have to know that the admittance is the inverse of impedance. It is important. And you have to know that how to combine two elements in series and in parallel. For example, in the series combination, suppose that you have two elements here, and no, it's parallel. For the series, you have one element here and one element here. That is the voltage source. We want to analyze this power system, this circuit. So if you present element 1 as an impedance Z1 and element 2 as an impedance 2 Z2, we can lump these two elements as a one element. Z is the summation of Z1 and Z2. It's the series combination of two elements. So if you have two elements in series, we can lump together in one element that is summation of the two impedance, Z1 plus Z2. Both Z1 and Z2 are complex value. And the final value, Z, is complex as well. However, if you prefer to work with admittance, it's different. You can present element Y, element 1 as a Y1, admittance 1, and the second element as a Y2. So if you use admittance for the representation, you can write this expression. It is very similar as a series, as a parallel combination of the two elements. You have to multiply y1 and y2 over summation y1 and y2. So it's another form. However, if you have a parallel combination, suppose that you have two elements and voltage source here. According to network theory, you can lump these two elements as a one component. If you use admittance, y1 here and y2 here, you can use this expression for the parallel combination. You can see here, we have a very simple expression for the parallel combination. So from these two expressions, we can say if we have the series combination, it's better to use the impedance because it's just summation of the two elements is enough. However, if you have the parallel combination, it's better to use admittance because you can use just sum to simple admittance. However, if you use impedance, it will be more difficult, but it's possible. It's based on your preference. However, the best way is to use impedance for series, admittance for parallel. For example, suppose that you have this circuit, very simple power system. You have a current source, you have a resistor, and you have an inductor in parallel. These two elements are parallel. But we want to know what's V. We want to calculate V if, oh my God, if the current source is sinusoidal function of time. It's I cosine function omega t. If it is the current source, what will be V? We want to calculate base of phasor domain, base of complex domain during a steady state condition. All of them are equal. So for the current source, we can write this equation. Do you remember before? For every sinusoidal function, we can write it based of this equation. It is complex value. It's the conjugate of complex value. And it will be the real part of the whole terms. I have to show you here. Suppose that in general, the complex value is A plus JB, a general term. We have two function. When I say RE, it means real. It means what's the real part of Z? It's the real part. It's A. Have imagine of Z will be this part. So when I write RA means real part, IM means imaginary parts. So we can show that the real part of this quantity will be IT, as we talked before, because every sinusoidal function can be summation of complex value and conjugate of complex value. However, for this power system, since R and L are in parallel, you can write in this way. Z is the power of R and J omega L. Since I talked that instead of L in a steady state condition, you have write J omega L. And instead of R, you have to just write R. So we have power R and J omega L. It will be the parallel. And if you use When you have two parallel, we talked about that before. A1, when it is parallel to A2, it will be A1 multiply A2 over A1 plus A2. That's why we wrote in this way. So we can say Z is the lump element. This one. You have Z, you have the amplitude of Z and the angle of Z. However, how we can calculate them? The amplitude will be this one. And this one will be the angle. So maybe it's better to show here. For example, we talked about that before. When you want to calculate amplitude and phase, you have here, we want to calculate the amplitude of this term. It will be the amplitude of this part, numerator and denominator, amplitude of this part. So the amplitude of this part will be R, omega, and L. However, this part is a full complex value. The amplitude will be the real part, square of real part, plus square of imaginary parts. That's why it's the amplitude of Z. And how we can calculate the angle of this Z. I want to ask you, suppose that one E exponential J0, not 1. What's the answer? Exponential J0, what's that? Equals to?
One.
Yes. Because when you have exponential J theta, it will be cosine theta plus J sine theta. And theta here is 0. If you insert 0 here, cosine 0 is 1, sine 0 is 0. So the imaginary part will be 0. Finally, we have just the real part that is 1. That's why we say EJ0 is 1. And what's the amplitude and phase of this value? It's a complex value. Are we agree? Z. What's the amplitude and phase? What's the amplitude of this value? Any suggestion?
Is it not also one?
Yes, it is 1. And what's the phase of Z?
0.
Yes, it is. So every real value, you have to remember that every real value has the amplitude same as that value, and with the 0 phase. For example, if it was 2, the amplitude will be 2, the angle will be 0. It's 2.5, the amplitude will be 2.5, the angle or phase will be 0. So for every real value, the angle will be 0. You have to remember that. And I have to erase this one. And maybe it can be interesting for you to show in the complex plane. You know, when I say E J0, it's 1. Its amplitude is 1. Its angle is 0. How can show it in a complex plane? You know, the amplitude, suppose that you are in an angle. You are in the circle. And you have a vector here that is rotate on this circle. And the phase difference between the vector here and this axis, suppose that as 0, is called angle. So when it is in a general case, E, J, phi. It is phi. And the amplitude is Z. Is right? So when we have 1 or exponential J0, we are here. It was the general case, but we are here. Just this one. It's exponential J0. If you have exponential J pi force, what's the amplitude? Can you guess? If it is Z, what's the amplitude of this expression?
1.
Yeah, the amplitude is 1. And what's the angle?
45 degrees.
Yes. Or 45 degrees. And how we can show it in the complex? Suppose that you are in a circle that is its radius is 1. So here is Z, this one. The amplitude is 1 and the angle is 45 degrees. It's okay? And suppose that we have 2 pi over 2. The amplitude again is 1 because everything is when is here is amplitude. Always here is amplitude. You are just changing the phase, not the amplitude. I started from 0, then pi force, pi second. So the phase will be pi second, and with the angle, it will be 90 degrees. and here, this vector, 1 exponential j phi second. So you can see it started from here and then rotate here and then here, again here. So it means that if you increase the phase, this vector rotate in this direction. So with changing the phase or angle, we don't change the amplitude, just change the phase. Okay, it was useful to know that. Let me to remove it. Okay. Okay, so now you can understand better this part. That when you have parallel, you can write this one as a Z, and amplitude of this Z will be this one. And the phase of Z will be this one, because it will be the angle of this one minus angle of this one. It is angle of j omega, and it is the angle of arc tangent omega L over R. It's the angle of this part. Okay. So when you can write this equation for the impedance, you have simpler power system. You have the voltage source, you have the current source, and an element that is Z with an amplitude exponential j phi, and it is the amplitude and it is the phi. So, and very simple, we can write voltage is impedance multiply current. You can see voltage is impedance multiply I. Do you remember we had in a simple power system, when you had R, just a resistor, you write very simple, V equal R multiplies I. Again, you can do it very simple, even with the inductor, because of the complex tricks we have. So we can write, we can say the domain analysis is the general form of circuit analysis when you have inductor and the capacitor in the power system. And then you can write the voltage. When you calculate the voltage, you can write in this way as a function of the time. And for example, it's the final answer. You can see if you have this current source, the voltage calculated across the inductor in the time function will be this value. And the phasor, I talked about that. The analysis that I have done is called phasor. Instead of time function, I use a complex value. You know, here I showed you for the power system with the current source, you have to apply the network theory methods to evaluate the system. However, instead of use that method, you can use complex value. That complex value is called phasor. Just the notation of phasor is the new notation that we use it, because every sinusoidal function can be written as complex value and the conjugate of complex value. And the impedance and the admittance are coming from this notation as well. You can understand better with an example. Do you have any question? Please stop me if you have question. Maybe with some example, you can understand better. So for example, here, you have a current source, you have a resistor, and you have the inductor. And the question gave us omega L is 2 ohm. So suppose that the current source is the sinusoidal function of time. You can write it in this way. However, for this part, we have two elements in series. We can write this equation. The whole impedance for these two elements is R plus J omega, because we define Z1, impedance 1, and Z2, second impedance. Since they are in series, we can say the final impedance will be Z1 plus Z2. And it is Z1 because the impedance of the resistor is just itself. And it is Z2, the impedance of inductor. So 1 plus J2 is the final impedance. And you can see it here. 1 plus J2, 1 is the real part. And if you add it with this part, because it is J2, because it's on the imaginary part, the final vector will be Z. It's the final impedance. And very simple case, you can write in this way. Voltage will be impedance multiply Z. You can see here, if it is I, it is I. If you multiply Z, the vector will rotate in this way, because this phase difference, because of the Z. Z is the complex value, and it has the amplitude and the phase. So we can say amplitude of V is amplitude of I multiplies amplitude of Z. And the phi, this difference between the voltage and current, will be angle of Z. You can see here the component of voltage as well. You can see the voltage is a complex value. It's the combination of the real parts and the imaginary parts. The real part is because of the resistor, and the imaginary part is because of the inductor. So when you suppose that if you have just the resistor in the power system, you don't have this part. If you have just inductor in the power system, you don't have this part. When you have together, you have just the real part and imaginary parts. Is there any question? So the next one will be the energy and power. So we can have 15 minutes break and then start the new topic, because it's new. Okay, so see you in 15 minutes.